All right, so for this one, we're going to do the transformations of the logarithmic functions, right? So those were the homework questions from last class. So we'll look at our logarithmic function transformations in this one, okay? So again, just like every other function we've done, we start by looking at the function, we look at the key properties, then we start looking at those transformations that can be applied, right? Yes, you've got your simple ones, but then you've got things that can be applied, your stretches, your transformations, your reflections, okay? And again, it's in that same form, right? You've got your a value that's out front. That's your vertical stretch, right? Your base is that c, right? That's not a transformation. That's just like the base of your logarithm, just like you had a base of your exponential, okay? Your horizontal stretches and translations are going to happen inside the argument of your logarithm, right? So that b value, once again, it has to be factored out, and it's going to be the reciprocal, right? So if you have a b value, that's your horizontal stretch, but again, it's the reciprocal, so it would be 1 over b. So if that b was a 3, your stretch is 1/3, okay? H there is your horizontal translation. Again, remembering to factor it out to accurately determine that translation. And then your k value that's been added after the fact, right, after the logarithmic function is done, that's your vertical translation. Okay, and then again, that's just going to shift your function up and down. Okay, and all of those, this would be like your base equation here. Your y is equal to log x base c, right, which would have come from your c to the power of y equals x, right? So switching that back into exponential form, that's what that would have looked like. Okay? So taking a look at this particular function, we're just going to try and sketch it ourselves. Without going straight to graphing technology, let's kind of come up with our table of values and get an idea of what's actually happening here. Okay? So looking at this particular function of y is equal to log okay, so we've got log x plus 9 as the argument, base of 3, and then plus 2. So what transformations have happened in this particular equation? Let's identify the transformations first. Horizontal. We've got a horizontal translation of minus 9, right? So we've got that ht of minus 9, and what's the other one that we have? Vertical translation of plus 2. Okay? So since we're not jumping straight to graphing technology, what's our best bet for graphing a function? Table of values, and we can get that table of values from a mapping rule. Okay? So again, if we create that mapping rule, any point xy on the original function would map to x minus 9 and y plus 2. On our new function, okay? So that requires, though, understanding what your base function would have looked like, right? So we need to look at what the base function table of values would be. So our base function here is just y is equal to log x base 3, okay? So in that sense, if we look at these values, if we tried to evaluate this function at 0, we tried to do log of 0 base 3. Will it work? You're going to try it. You can take out your calculator. You can do log of 0 divided by log 3. But it's
0, aren't you? Or the 0 on top.
Well, it's kind of what's happening is you're trying to say what to the power of 0 equals 3. Nothing, because anything to the power of 0 is actually just 1. So it's undefined there, right? Because you have in a basic logarithmic function, like we kind of talked about before, is that function looks like this, right? Does the function exist at x equals 0? No. So at 0, it's actually undefined, right? We have a vertical asymptote at x equals 0, okay? What about at 1? What's our function do when x is equal to 1? What's the y value? The base function.
0.
Okay? So you're doing 3 to the power of what equals 1? 0. Right? That's how you're kind of solving this, right? Because if you put this back into exponential form, this is like 3 to the power of y equals x. Right? So if we're giving that x value is 1, 3 to the power of what equals 1? 3 to the power of anything, or so anything to the power of 0 equals 1, so 3 to the power of 0 is going to equal 1. So your next point that would make the most sense is to say, okay, well, what if y was 1? What would x equal? 3. Right? Because you do, if x was 3, you do log 3 divided by log 3, and you get 1. Right? What if y was 2? What would x be? 9. Right? So again, converting that base logarithm into an exponential kind of allows you to create your table of values a little bit easier going backwards, getting your y values and then moving that way. Okay? We can do one more. If the y value is 3, what will the x value be? 27, because it's going to be 3 cubed. Okay? So that would be our good base function table of values. And then all we need to do is apply the mapping rule to that base function. Okay? So we'll apply that mapping rule. So for every x, y coordinate point, we'll go x minus 9 and then y plus 2. Okay? So our new function, right, would be at negative 8. Right? So we won't look at that 0 undefined function just yet. Right? But we'd have negative 8 and 2. Then using the 3, 1 point, 3 minus 9 is going to be negative 6. 1 plus 2 is 3. 9 minus 9 is going to be 0. And then 2 plus 2 is 4. And then 27 minus 9 will give us 18. And then 3 plus 2 makes 5. Okay? Where will the vertical asymptote be? Vertical asymptote. At minus 9. Right? Because your vertical asymptote is this straight up and down function. Right? So if we have this horizontal translation of minus 9, we're going to shift that asymptote back 9. So in this one, we're going to have a vertical asymptote at x equals minus 9. Right? So using those points, we can then graph our function. Right? So here's that vertical asymptote at x equals minus 9. And then we just start using those point values. Right? So negative 8 and 2. Negative 8 and 2. Negative 6 and 3. Oops. Right. 0 and 4. Go there. And then 18 and 5. So that one's clearly not on the graph, right? But again, if this is going to be our vertical asymptote, we know that it's going to shift down and come this way, and then it's got this slight curve going up like that, right? And off it goes. So that would be like a very rough sketch of what that function is going to look like, okay? So again, we've identified that we've got this vertical asymptote here at x equals negative 9. Okay, so you've got your x equals negative 9 vertical asymptote, and then you've got a y-intercept at 4, right, which we saw, and then you've got an increasing function, right? Domain would be x has to be greater than negative 9, range would be any real number. Okay, so I mean that's kind of again what they're talking about, right? So in part B, the equation of the asymptote, x equals negative 9, domain, x has to be greater than negative 9, range, any real number. Y-intercept we found when we did our table of values there, so it's at 4. Right? Now, how would we find the x-intercept, though? We know that it exists based on the graph. How would we solve for it? Right? I mean, yes, if you graphed it using graphing technology, you could just, find it that way. But let's take a look at trying to solve for it. So our new function was y equals log of x plus 9, base 3, and then it was plus 2. Okay? So when you solve for an x-intercept, what's the very first thing you do in any equation? Solving for an x-intercept, we set y equal to 0. So we set our function equal to 0. So we're starting now dealing with our solving using logarithms, right? So log base 3 x plus 9. Okay. Yeah. This is the glitch where if the video is any longer than like 4 minutes, it decides it doesn't like to work. Okay. So how do we start solving this?
Subtract 2.
Subtract 2 from both sides. So we then get negative 2 is equal to log base 3 of x plus 9. And how do we solve for this? This,
Log 3.
do what?
Divide by log 3.
No, so we can't divide by log 3. Okay, so while that might be instinctual, again, this is, logarithms is an operator, just like what sine and cosine is an operator. You can't divide by sine. Let's convert it. Right, yesterday we spent time practicing converting between exponential to logarithmic. So logarithms are used to solve for the exponent in exponential, and we can convert this back into exponential form to solve for x here. So the base of your logarithm is always the base of your exponent. So in this case, it's 3. Okay? What was isolated becomes your exponent. So this is now 3 to the power of negative 2 is equal to the argument of your logarithm. Okay? That is how you do the conversion. Okay? The base of your logarithm becomes the base of your exponent. What once was isolated is now the exponent, so that negative 2 is the exponent, and it equals the argument. Okay? Notice how that gives me x by close to by itself. Now all I need to do is subtract 9. So, what is 3 to the power of negative 2? Remember your exponent laws. That's the same as 1/3 squared. Right? When your exponent is negative, you take the reciprocal of the base, so 3 becomes 1/3, and then your exponent becomes positive. So that's 1/3 squared, and then minus 9 equals x. So what we end up having here is 1/9 minus 9 is equal to x. And that can be either done as fractions or decimals. So if we wanted to keep this as fractions, we would take this as 1/9 minus 81 over 9 equals x, and 1 minus 81 is going to be negative 80 over 9 is equal to x as your most exact value there. Right? So again, we use that being able to transform from one form to the other to help us solve for values of x or values of y. Okay? All right, so what about this one here? What if we have y equals negative log of 2x plus 6 base 2? Let's start by identifying transformations here. What have we got?
Factor the 2.
So, thank you very much. So that is definitely what we need to do. In order to correctly identify the horizontal stretch and the horizontal translation, we need to factor out the 2 out of this argument. So this is now going to be 2 times x plus 3. All right? So what that means then is that since this b value is 2, that means we have a horizontal stretch of 1/2. Right? And now that it's been factored out, we can accurately determine that we have a horizontal translation of negative 3. Right? What does this negative out front mean? It's going to be a reflection in the x-axis. Right? So our curve is going to flip, okay, across that x-axis. So again, if we were to try and look at a mapping rule, right, that mapping rule xy would map to 1/2 x minus 3 negative y. Right? So once again, in order to utilize your mapping rule, you need to take a look at your base function and your base table of values. So your base function is that y is equal to log x base 2, right? Which again, if you think about that, putting it back in exponential, 2 to the power of y is equal to x. So if we look at that base table of values, right, once again, at 0, we're undefined. That's where our vertical asymptote is. Okay? If y is 0, right, so 2 to the power of 0 is 1. If y is 1, x is 2. If y is 2, x is 4. If y is 3, x is 8. Right, so you're kind of doing the table of values backwards because that's the easier way to do it, unless you want to sit there with your calculator and actually calculate values of logs. Right, but these give you your better values, like what we did with radical functions. Right, so if we were to then map this, okay, again, we don't really need to worry about that asymptote value because we just know that our new asymptote is going to be at x equals negative 3 because that's where our horizontal translation is. Let's just take a look at these points here. So our x value is that 1 needs to get multiplied by 1/2. So that's 1/2 minus 3. So that's going to be negative 2.5. And that value is still just going to stay at 0, right? Because 0 made negative is still 0, right? 2 divide it by 2 or multiply it by a half, it's 1. 1 minus 3 is negative 2. 1 make it negative, it's negative 1. Okay? 4 times a half is 2. 2 minus 3 is negative 1. 2 make it negative, there's my negative 2. Okay? 8 times a half is 4. 4 minus 3 is 1, and 3 make it negative. Right? So these are my points that I now have to enable me to sketch my function. Right? And apparently I already had that table of values there, but all good. Right? So we just talked about the horizontal asymptote, or the vertical asymptote, sorry, would be at negative 3, because that was where the transformation was. Right? So we know that's that transformation. And then if we go back and look at our points, so negative 2.5 and 0. So there's that point there. So we have the x-intercept in that case. Negative 2, negative 1. Negative 1, negative 2. And 1, negative 3. So again, because of that reflection, our logarithmic function actually goes up this way and then comes down like this, right? Because we've had that reflection across the y-axis. Okay? So again, if we wanted to talk about this, we've got that vertical asymptote at x equals negative 3. Okay? Our domain is just going to have to be x has to be greater than negative 3. Our range can still be any real number, right? We have our x-intercept we solved for, right? And that was at negative 2.5 and 0. And if we needed to find the y-intercept, it's just a matter of setting x equal to 0 and solving, right? So in that case, it would just be a matter of doing y is equal to negative log base 2, 2 times 0 plus 3, and calculating that, okay? So that would be log 6, right? And this would just be a calculator question where you would have to do negative log 6 over log 2, right? So if we do that very quickly, log 6 divided by log 2, and then make it negative, you've got this value at negative 2.58. Right, and that looks like it's approximately correct, right, at that negative 2.58 right there. Okay, so these are all these ways we can graph given those transformations. So just like we've done this again before, once you have your graphing down, you then look at the graphs and try and determine what your transformations are. Okay, so looking at this, the red graph is generated by stretching the blue graph of y equals log x base 4. So they're telling us that that blue graph has an equation of y equals log of x base 4. Look carefully at the graphs. What seems to change? Or what stays the same? So, yeah, the red graph seems to have been shifted up, for sure, right? Or it could be, but yeah, the question actually says generated by stretching. So they're already telling us that it's either going to be a horizontal stretch or a vertical stretch. So what I tend to look at here is the fact that this point here, the x-intercept on both of those appears to have changed. So if the x-intercept is what changed, does that imply a stretch horizontally or a stretch vertically? If the x-intercepts change. Horizontal, right? If the x values change, that indicates a horizontal stretch, right? You can even look at the points they're given here on the graph. You've got this point here at 4, 1, and you've got this point here at 1, 1. The y value has stayed the same. The x value has been what's changed. So since it's the x values that appear to be changing, we can apply that it's a horizontal stretch. Horizontal stretch of what? Yeah, so I've gone from a value of 1 to a value of, well, actually, the original graph was in blue. So we've gone from 4 to 1. So it's actually a quarter. So my horizontal stretch is a quarter.
Why is it not a horizontal translation?
Why is it not a horizontal translation? If there was a horizontal translation, then the asymptote would be different, right? Because where it shares the same asymptote, it means it hasn't been shifted front or back. And specifically, the question did say a stretch, right? They've kind of given us that hint that we only want to deal with which can be done by stretching, okay? So we've got this horizontal stretch of a quarter because we've gone from 4 to 1, right, through multiplication, which means when we go to put that back in our equation, that b value that we're going to use is the reciprocal of a quarter, which is 4. So that would be my equation of my red graph, right? So look at the things that are stayed the same, look at the things that have changed, right? So when we look at this, the vertical asymptote hasn't changed. So that indicates that there's been no horizontal translation, okay? And the X intercept has changed, right? So that indicates that there's been a horizontal stretch. The X values have been affected and not the Y's, okay? So final example, we'll take a look at a word problem, and that'll be that. Okay, so welding, most common way to permanently join metal parts together. Welders wear helmets fitted with a filter shade to protect their eyes from the intense light and radiation produced by welding light. The filter shade number n is defined by the function n is equal to 7 times negative log t over 3 plus 1, where t is the fraction of visible light that passes through the filter. Shade numbers range from 2 to 14, with a lens shade number of 14 allowing the least amount of light to pass through. The correct filter shade depends on the type of welding. A shade number 12 is suggested for arc welding. What fraction of visible light is passed through the filter to the welder as a percent to the nearest 10,000th? Okay, so a lot of background information there, but ultimately we need to take a look at the equation that they've given us. Right? They've given us a function of the shade number as a function of t, which is the fraction of visible light that is passing through. So in the ultimate question, what information have they provided us with? Have they given us the shade number, a value of n, or have they given us the fraction value of t? Reading that last line there. They've given us the n value. They've given us that the shade number is 12. So they've given us an n value, so that 12 needs to be substituted into our formula for n. Right, so 12 is now equal to 7 times negative log t all over 3 plus 1. And our job at this point is to rearrange this equation and solve for t. What's my first step? Subtract 1. Right, so we subtract 1 from both sides. We get 11 is equal to 7 times negative log t all over 3. Next algebraic step. Multiply both sides by 3, so now we have 33 is equal to 7 times negative log of t. Next step, divide by 7. So now what I have is 33 over 7 is equal to negative log of t. You could then divide by negative 1 and have it as negative 33 over 7 is equal to just log t. But now how do I get the t by itself? We've already said we can't divide by log because...
What's the log of 1?
So if there's no base given, it's assumed to be in base 10. Right? Because logs are programmed as base 10. So if you don't see a base given in the equation, we know that instead it's base 10. So this is where we rearrange.
T equals 10 to the power of negative 33.
T is equal to 10 to the power of negative 33 over 7. That is correct. Right? So at that point, that's just a calculation we'll have to make, right? 10 to the power of, make sure you put that exponent in brackets, of negative 33 over 7. And that then equals, t is equal to 0.0000193. Okay, but remember, t represents a fraction of light that gets through, and it's asked us to find it as a percent. So how do we turn fractions into percents? Multiply by 100. So I'm going to take that value, and I'm going to multiply it by 100. And now it's just t is equal to 0.00, and it said nearest 10,000th, so that's tenth, hundredths, thousandths, 10,000ths. So 0.0019%. So that's the amount of percentage of light that's actually getting through that filter, right? That shade filter if you're of your welder's mask.
When you put the 10 as the base,
Yep.
why does it get rid of the log?
Why does it get rid of the log? That's just the relationship between logarithms and exponentials. Like it's the undoing operation, just like, yeah, might be a good idea. Okay, so it's that rearrangement, and the same thing if I have the exponentials, when I turn it into, the log appears. Right? So it's that relationship between doing that inverse. If you want to try and isolate an exponent, you have to use logarithms. So then the logarithms go away when you go to putting it back into that exponential form. Okay? So that's your transformations of logarithms, and there are your homework questions.